Hello, my name is Karlo Jukic, and this is Lab 4. For introduction, Phys labs predict current circuit behavior with resistors and capacitors, and use multimeters to measure values, currents, and differences between circuits, and to utilize principles of current and energy conservation. For our main results, our RC calculated came out to 7.75 seconds. Our current came out to a measured 0.0187 amps, and our node and loop rules applied. Our fundamental principles, we have Ohm's law, where current through a conductor between 2 points is proportional to the voltage across those points, and that's just V equals IR, the basic equation. And you can also be represented by that triangle, often is. Our node rule, current flowing to a node must be equal to the current flowing out. So self-explanatory, all these currents in must add up to all these currents flowing out, equals 0. And our loop rule, sum of all electric potential differences around a loop is 0. Take the voltages at all these points, they should all add up to 0. Our experiment predictions, our system is our circuits, and our surroundings is everything else. We have two resistors, one of 47 ohms, one of 100, two ammeters, and two 1.5 volt batteries. Therefore, plugging these all into our equation, our current should be measured out to be 0.0204 amps. We set this up in real life. We have an RC circuit of two ammeters, two 1.5 volt batteries, and two resistors. Our recorded value for our circuit was 0.0187 amps, and it was the same flipped, but just negative. And then when a voltmeter is introduced, the ammeter read 0, while the voltmeter read 3.07, is because when you introduce a voltmeter directly into the circuit, it breaks it. The current no longer flows, but you can still get a voltage measure across it. And when you take out the voltmeter, place it with the wire, and then use little tongs to measure the voltage across the points, the current would come back. So after closing the circuit on experiment 1, the voltmeter using the tongs was measured. For our points on AB, we got 2.87. C to D had negative 0.99, and E to F had negative 1.79, and everywhere else had 0. And this total adds up to a total of 0 volts, which means our loop rule applies. Here's our graph of potential, starting with our two batteries. That's what this little divot is. That's the first battery. That's the second battery. Going into the C location, our first resistor, our potential dips a little bit, and then our second resistor, which is much greater in resistance, dips all the way back to 0. Our experiment 1 calculations for our real resistance values using this equation, V at the location divided by our current. So we had our going from D to C, not C to D, that's why it's positive. We have a real resistance of 52.94 ohms. At the 100 spot, we had a resistance of 95.72 ohms. And our wires had 0 and our ammeters had 0 because there was either no voltage at those points or the ammeter was not strong enough to detect a voltage at those points. For experiment 2, we set up a circuit of one light bulb that's either 10 or 20 ohms, one 9 volt battery, and one capacitor. Once connected, the capacitor discharges and dims the light bulb for both, with the higher resistance bulb taking longer. Here are charge and discharge times. And higher resistance capacitor, or the higher resistance light bulb is going to take longer because more resistance from the circuit. Experiment 3, we set up a smaller circuit with a battery and a 47 resistor, and then we'll measure time over voltage across that circuit and plot it on a graph to get our RC. And we calculate to be current times ohms, or capacitance times ohms, which is 0.2 times 30 ohm to get a predicted value of 6 seconds. And we actually plot this graph using this equation down here. We plot our ln of V over V naught and linearize this to get a slope. Apologies. So we can then plug that into this equation, calculate for our RC value by plugging in 1 second for our time, and we get an RC 7.75 seconds. Our discussion, our model and estimated values were somewhat close. Some source of error could be human error on the circuit setup, a faulty emitter or ammeter, which we actually had to replace one mid-lab. So our second part of our experiment came out much nicer than our first. And fault to out-of-tolerance circuit components, things like wires having some resistance where it should, ammeters, or just bad resistors. Or what ifs? What if we used the virtual circuit link that was in the last labs, and that the simulation would just behave incredibly ideal, no ammeters, no wire resistance, current was perfect, so were voltages at the points. It really worked out very beautifully. And our second what if is that we use an ammeter to measure how long it takes to charge a capacitor. Why the measured time is different from predicted time, and that's because measured time varies as the capacitor can either discharge or not charge fully, and any residual resistance that's still in the circuit. So things like wires or, again, the ammeter giving some slight resistance affects this actual time. Thank you for watching.